Hello, can you hear me? Welcome everybody. Today's the third and most exciting day of the summit, and I'm glad to see all of you folks showed up here to hear about some of the challenges that are being faced in the telco cloud, particularly around delivering accelerated data performance in an environment with heterogeneous compute models. So with that, let's embark. I just want to share a little bit about our experiences and some of the work we've been doing at Nuage Networks, and provide a few working demos for you to see how things actually behave. Some of this is slightly repetitious to a talk we did earlier this week, but there is some new material here, so please stick with me. So when we think of the telco cloud, there's several interesting trends moving in the marketplace right now. Both from a technological point of view and also from a business point of view. The telco cloud is evolving quite a bit from a pure VM-oriented type of deployment to a containerized deployment. And there's a very strong desire to move to an environment where everything is completely cloud native and which has a lot more flexibility, a lot more efficiency in terms of deployment characteristics. Also, in the telco cloud, the performance requirements for the data plane are often very extreme. The number of packets per second you have to deal with is often measured in millions of packets per second. Often they're very small packets, and so that provides a daunting challenge to the traditional VirtIO oriented types of virtualization. And then beyond that, people want containers to be able to deliver the same level of performance that we're able to achieve by accelerating the data path for VMs. And that's really kind of at the heart of what I'd like to share with you today, is how we're achieving that at Nuage Networks. And finally, there's a problem where, even though everybody wants to move to a containerized workload environment, it's not going to happen overnight. And anybody who's been in the telco business for any amount of time knows there's a lot of legacy stuff around that lasts almost forever. And so the transition from a virtualized, VM-oriented VNF type compute workload to a purely containerized CNF type of workload will happen only over time. And so you must be able to deal with a heterogeneous compute environment. And so this is a growing challenge, this tension between wanting to have accelerated data paths and also at the same time having heterogeneous types of workloads going on at the same time. So how do you deal with that? Well, fortunately, there are at least several vendors, certainly Nuage Networks is one of them, who has the ability to provide an SDN solution that can work with a heterogeneous set of workloads. And so conceptually, what these SDN solutions do is create a virtual network that sits on top of your existing leaf-spine physical network environment. And in the case of Nuage Networks, we're able to deal with a wide range of different compute environments. To be a little more specific, our product for cloud networking is called the Virtual Cloud Services, or VCS. VCS can work with physical or bare metal systems. You can do hardware VTEP. You can do virtual machines for things like VMware with KVM. So that's more or less the OpenStack type of environment. And also for Azure for Hyper-V. We also support containerized workloads for things like Kubernetes, OpenShift, and so on. And then also we have support for connectivity into the public cloud. So through a single network management system, or through a single network management pane of glass, you can actually be organizing and orchestrating all the rules and the flows of traffic between all these different types of compute environments. So it's a very rich and very diverse environment that we're able to address. So the VCS is actually part of a bigger constellation of products that Nuage offers, and I just thought I'd mention that because we're basically controlling the network, then that gives us an opportunity to do other things. So we can do SD-WAN, for instance, creating IPsec tunnels between remotely located data centers and branch offices. So that also fits into this picture. And also, maybe more importantly, we can do analytics against all the traffic that's flowing through the network. And so, we also have virtualized security services, which monitors traffic and provides a mechanism for creating alarms and taking action when you see peculiar behavior happening on your network. All this has to be automated. So in terms of accelerating the data path, Nuage actually has multiple approaches to doing this. And some of these are probably more obvious than others. First, maybe in the middle here, I should mention the traditional point of view, or the approach, which is basically just using VirtIO, or using kind of a traditional kernel interface to OVS. And this is kind of nice because it's very platform independent, and it's pretty easy to deploy. In the case of Nuage and probably a lot of other SDN solutions, they just use the kernel plugin for OpenVSwitch that comes with the distro. So you don't really have to worry too much about compatibility from release to release. So that's kind of a nice approach. But the huge drawback, and which I'm sure most of you are aware of, is that performance is really a challenge. So to mitigate or to overcome some of those challenges, there have been different schemes created. OVS DPDK is one of them. So in that approach, basically you take a bundle of cores, set them aside, and run a dedicated embedded application that takes care of all your data plane work and then provides data service to the rest of the system. And that approach is actually pretty good, and it's in production. The only limitation really is that you have to dedicate a fraction of your host to doing that other work. And that work is that set of resources that are set aside for DPDK is fixed no matter what workload you have going through. So even if you only have 1 packet per second coming in, if you set aside 6 cores or 10 cores or whatever, those guys are all gone. They're just off doing nothing, waiting for a packet to show up. So it has its limitations, but it also is a very tractable solution. And then another approach is just to depend on an external VTEP. So you can get a switch or Tor that, for instance, has the ability to take a VLAN and then turn it into a VXLAN packet and send it out on the larger fabric. So that approach is also in production. It works well. But the approach that seems to be getting most of the interest right now, and which has probably the best promise in terms of cost, in terms of performance, and in terms of flexibility, is the use of what's called SmartNICs. There are different terms that have been kicked around. I don't want to get into a semantic discussion, but basically it's a NIC which has a switch built into the NIC itself. And so if you have OVS running, you can actually use OVS to program that switch, and the switch then takes care of all the work that would have been done by the kernel. And because it's done with a highly efficient ASIC, all the implementations we've looked at, which is probably 1 or 2 at most, but it is an emerging market. The performance numbers are truly remarkable. And we've documented that and shared that with the OpenStack community at several different presentations we've done previously, mostly using OpenStack. But now the challenge becomes, how do you bring that to a heterogeneous environment, particularly something that's containerized? So to enable all this, first off, we had to modify our implementation of our SDN. And maybe I should just quickly go through the way we're architected. So like most SDN solutions, it's a 3-layer solution. At the top level, you have a management engine, which has a RESTful API, so you can program it. You can use that to create rules. You can use that to orchestrate the way things are being deployed. It allows for automation. And then that communicates with an SDN controller, or maybe multiple SDN controllers. In our case, we've actually virtualized the software that's inside of our service routers to do that. And then at the compute level, we're using OVS, primarily OVS. And OVS had to be modified in order to take advantage of this switch on NIC capability. So we've modified our OVS implementation, which is tracking very closely with what's upstream, but a little bit we stay just a little bit behind, to be conservative and to avoid, any of the turbulence that comes with new stuff that's getting put into the upstream code base. So we've created something we call OVRS, which is offloaded virtual routing and switching, and that's the lower box here in our architecture. Now, how this works, from the standpoint of a container or a pod or even a virtual machine, there's SRIOV, which creates virtual functions. So it basically takes your hardware interface and fractionalizes it. So you get a chunk of the bandwidth that's available to the physical NIC, and that little chunk of virtual function is passed up directly, bypassing the kernel to the container itself. So the container or the VM has the ability to do compute node directly with the NIC. But the problem there is, you may not know what to do with those packets when they come down through that VF. And that's what the eSwitch does. So the switch on NIC is programmed and knows for each VF what to do. So that's really the key to how all this works. And part of the trick is once you turn on the switch on NIC, there's a representer and also the physical VF name. So there's a netdev and a representer. So the representer is given to OVS. It's a pointer, basically, that tells OVS what rules to apply to a particular VF that's actually attached to the eSwitch down below. So that's, functionally how this all works. So in terms of deployments, when a packet comes in initially, as you can see from here, in a more traditional model, you hit the kernel, and then the kernel doesn't know what to do with the packet, so it sends it up to OVS or to vSwitchD, and it gets the correct rules. And those rules may actually come from the management engine and through the controller. So there's a chain of things that have to happen. In the case of the eSwitch, similar things happen. So you have a packet that comes in, you don't know what to do with it. The eSwitch consults the kernel, and the kernel consults vSwitchD. And then the vSwitchD is actually using kernel modules to do TC to the eSwitch and also talking to the kernel as well to program the flow inside the kernel. So there's always a fallback. If the eSwitch fails or doesn't know what to do with a packet, you can always process it in the kernel as well. So there's two different data paths. They try to stay in sync as much as possible, but there's a very logical fallback mechanism. So in essence, that's how things work. And an important thing to understand, and you'll see this in the video I'm going to show here in just a moment, when you have a packet that's being processed in the eSwitch and it's going through the virtual function, it's never seen by the kernel. So if you run TCP Dump, for instance, against that interface, you'll see the first packet show up or the first time that packet comes through because you're learning the flow. Once the flow's learned, you never see it again because it's all expressed directly from the NIC all the way up to the container. So to make this work with Kubernetes or a containerized environment, in fact, in general, to work with any kind of cloud management system, you have to have a plugin. And so Nuage has developed a plugin for Kubernetes. The way these things work is pretty straightforward. We're using XMPP protocol to orchestrate between our management engine and our controller. We use OpenFlow, as you might expect, to program OVS. And then we have a RESTful API, which allows the plugin to consult and advise and coordinate with the SDN controller. And so the way this actually works in real life, you decide you want to launch a pod if you're using Kubernetes. Kubernetes has information about policies that you want to apply. So it consults with our management engine up here, and programs the zones or the domains or the subnets that are going to be used. It applies the security policies that have been dictated by Kubernetes, and then that information is also used to launch the pod. Once the pod's created, there's a monitor on the compute node that actually detects that event, and it consults with our controller for information about what to do with that particular pod. And all that information has already been pre-programmed over here when the initial request came through the Kubernetes interface. So in essence, that's what a plugin does. It provides coordination between Kubernetes, the launching of a pod, and the SDN controller. And it's really kind of a nice arrangement because it helps you maintain consistency between two different methods of programming rules for the network. So I'm going to show you a quick demo of how this all works. We'll put it all together. In this demo, there's actually 4 compute nodes. One of them is sort of a service engine. It has all of our management stuff and control stuff running on it. And then, like any typical Kubernetes deployment, there's a master and 2 minions. Between the 2 minions, we'll actually have VXLAN tunnels, as you would typically have in an overlay networking environment. And then I have 2 different combinations there. So one is accelerated and one is not. And then we'll compare the throughput using both IPerf and T-Rex and test PMD to look at how throughput varies depending on whether or not you're using a slow data path through the kernel or a fast data path through the eSwitch on the NIC. Okay, so with that, let me show you the video you've all been waiting for. Gosh. Once again, I have a problem here. Okay, hold on. Let's rewind here and start over. Sorry. All right. Sorry about that. So this is actually joint work that was done with Mellanox. And Mellanox has been a tremendous partner for Nuage, and they've really provided a lot of the technological leadership in the marketplace to enable this whole concept of switch on NIC. This is our GUI, our web GUI that we provide for controlling our SDN deployments. This is looking now at the underlay to see all the different ports that are attached, the things that are physically attached. Here you can see the representers on the right. These are actually the VFs, the net devs that are associated with the different SRIOV VFs. Now let's take a look at the overlay. Here we've defined a virtual network with certain rules, and some of this is automatically created by the plugin. So when Kubernetes receives a request to launch a pod, it programs our controller and it shows up here on the overlay. And this is just showing ports that have been created. And also, if you look at OpenVSwitch, it's important to set the fact that you're doing hardware offload. If you forget to do that, none of the offloading will actually happen. And with that, let's run a couple tests. So first, we'll start off by just pinging and doing TCP dump. And as you can see, the packets are showing up with TCP dump. This is the non-accelerated data path. Okay. And then secondly, we can look at the flows. If you look at these flows that are being dumped, these are the active flows. There's no indication there that these are accelerated. They look just like standard flows. Okay, and finally, we can run IPerf or netperf to get throughput and latency numbers. So unaccelerated, we're getting around 14 gigabits per second on a single pair of containers and a single thread of compute. And same ways for latency, we're seeing, I forgot the number, but I'll show it to you at the end here. Okay, here now we've switched over to the accelerated data path, and you can see when we do TCP dump, there's only one time that we see the packets come through. After that, they're offloaded, everything's expressed directly from the NIC all the way up to the container. Okay, and then the flows will actually show you that they're hardware offloaded. So if you dump flows, you can actually find out whether you're actually getting the benefit of the offloading. And we look at throughput here, we're getting around 21.7 gigabits per second on a 25 gig link, so that's quite a bit faster than what we were seeing previously with the kernel interface. And the latency is also a little bit lower. Okay. So just to summarize, this is what we've solved. The throughput jumped roughly 50% when we turned on the accelerated data path, and this was using IPerf. So IPerf is going through user space, and it really hides a lot of the benefit that the accelerated data path delivers. And likewise, we see about a 40% reduction in latency. So that's also goodness. So that's just saying, like, for any typical user application, doing nothing special inside the container, you're actually going to experience a higher level of throughput. But the differences are much more dramatic if you run a DPDK app inside of your container. So for instance, here we ran TestPMD with T-Rex. TestPMD is a popular forwarding app. It's an L2 forwarding app that's provided with the DPDK library. T-Rex is also widely used for generating packets. And you can see here that we're able to generate 23 million packets per second. These packets were around 110 bytes per frame. So that converts, in terms of line speed, that's very close to 25 gigabits per second when you include the 50-byte VXLAN packet header. So, and also you can see almost no loss. Bidirectional performance, it's like 23 million packets per second in both directions. So this would be at least 20 times faster than what you could get by using the kernel module. It's very difficult to hit more than 1 million packets per second using a user interface, typical user interface. So anyway, that's our demo. We've delivered a heterogeneous compute environment that supports an accelerated data path, and we're forging the way into the brave new world of the telco cloud. So thank you, everybody.